Hello everyone, welcome to my presentation. My name is Xiuheng Wang, a PhD candidate at the University of Zurich. In this presentation, I will introduce you our recent work about online change point detection on Riemannian manifold with Karcher mean estimate. This is the joint work with Ricardo, Borsoi, Cédric, Ricardo. Let's start with what is change point. As you can see in this figure, change point are time index when there is a change occurring in the state of the time series measurement. Change point detection has been studied in Euclidean space with a long history. However, more and more signal processing tasks has considered the signal which is in non-Euclidean space. In particular, Riemannian manifold has drawn significant attention. Riemannian manifold has a large range of applications. For example, in medical field, it can be used for modeling the signal from the diffusion tensor imaging. In the graph signal processing, it's a very powerful tool for graph embedding. It's also very useful in video analysis, especially in pedestrian detection. As one can imagine, developing method on the Riemannian manifold is very promising. However, it's also very challenging at the same time. That is because, first, the geometry of the Riemannian manifold is nonlinear. Second, Riemannian manifold doesn't have the vector space structure, which makes it harder to generalize the approaches designed for the Euclidean space. Fieldwork has investigated manifold-valued data. For instance, an online change point detection algorithm was designed for the compound Gaussian distribution. This is parametric and not broadly applicable. An example of the non-parametric technique is only able to detect a single change point in an offline manner. In this work, we introduce a unified framework for online change point detection on Riemannian manifold, which is non-parametric at the same time. Now let's formulate the problem of change point detection. Assuming that time index TR, where is that change in the probability measure of xt lying on the Riemannian manifold. We say TR is a change point. The change point detection problem consists of estimating TR with the following requirement: high detection rate, low false alarm rate, and low detection delay. Before discussing our method, I would like to give a brief introduction about the Riemannian geometry and optimization. A Riemannian manifold is defined by a constraint set equivalent with a Riemannian metric. Look at this figure. It illustrates the Riemannian manifold and the Riemannian distance between 2 points on the manifold. The tangent space is defined as all the velocity from x, and the exponential map is defined from the tangent space to the manifold. The curvature of the Riemannian manifold is introduced by two factors: constraint and the Riemannian distance. For example, we can define the space of the symmetric positive definitive matrix as a Riemannian manifold with a special designed distance. Now we turn to the Riemannian optimization. There are two very important tools: Riemannian gradient and retraction. Look at this figure. It illustrates the procedure of the gradient descent on the Riemannian manifold. At each iterations, we compute the Riemannian gradient and multiply it with the step size. And then we can retracting them back to the manifold. In the end, it will converge to the optimal value. Here, I give more details about a typical Riemannian manifold, the one of the SPD matrix. You can find the Riemannian distance, gradient, and retraction. This will be used in our experiment. In this work, we focus on non-parametric strategy, where there is no prior knowledge about the probability measure of the data stream. In Euclidean space, it can be done by the monitoring change in the mean and variance, or in a generalized statistic. In order to generalize such strategy to Riemannian manifold, we consider the Karcher mean, the minimum of the expected variance of the Riemannian distance, which is unique in many manifolds, including the Riemannian manifold of the SPD matrix. To achieve online detection, we consider using the Riemannian stochastic gradient descent algorithm to address the problem defined above. On the Riemannian manifold, The update of the Karcher mean with the step size f is given here, where h denotes the stochastic gradient of the loss, which is unbiased. For computational simplicity, we replace the exponential map by a retraction. As discussed above, we aim to detect the change point by monitoring abrupt change in Karcher mean over time. This requires knowledge of the two quantities, the Karcher mean of before the change point and the Karcher mean after the change point. To detect the change point, first, we compute the estimate of this value, and then, as a test statistic, we propose to compare the two quantities using the Riemannian distance. The rationale is that the larger the Riemannian distance, the more likely to flag TR as a change point. Now there's one question left: how to calculate the Karcher mean before change point and after change point in an efficient and online way. To answer this question, we consider two Karcher mean estimates with two different step size lambda and capital lambda. Convergence is directly affected by the step size. We put a constraint that lambda is smaller than capital lambda. This means that the Karcher mean with capital lambda is more adaptive to new data and approximated the Karcher mean after change point. The Karcher mean with a small step size lambda has a longer memory and is more suitable to estimate the Karcher mean before change point. Now we can design an adaptive change point detection statistic. That is, the remaining distance between these Karcher mean estimates. Then, change point detection can be performed by comparing the statistic to a given threshold. Now we turn to present some experiment on the Riemannian manifold of SPD matrix. With a series of SPD matrices lying on this manifold and the Riemannian distance, the Karcher mean can be estimated by minimizing the following cost function. We compare our method with two baseline algorithms, namely NUMA and FCBD. NUMA is designed for the Euclidean space and is online. FCBD is designed for the manifold-valued data, but is offline. We first conduct some experiment with synthetic data. The metrics are sampled from a Wishart distribution. We put a change point by resetting this distribution. This figure shows the ROC curves of all the methods for 5,000 Monte Carlo runs. It can be seen that our method achieves the best performance compared to the NUMA, which doesn't take the manifold geometry into account, and FCBD, which is designed to operate offline. To further evaluate our approach, we make use of a real video. We consider detecting change point in disjoint and compacted region of this scene by segment each frame into subpixel using Cédric technique. A snapshot of this scene with its subpixel decomposition is shown in this figure. In each frame, we compute a feature vector for each pixel. For each region, the covariance descriptor was a SPD matrix lying on the Riemannian manifold. The resulting test statistic for one given region is shown in this figure. We can observe that all the peaks are located near the change point, which indicates a good performance. In conclusion, in this paper we present a unified non-parametric and online change point detection framework on Riemannian manifold. More specifically, an adaptive detection strategy is designed by comparing two Karcher mean estimates. Karcher mean estimates converges faster and to be more adaptive to new data. And another Karcher mean estimate converges more slowly and focus on the long-term trend. In the future work, we will do the theoretical analysis, including convergence, performance guarantees, and so on. At the same time, we will apply our method to other Riemannian manifolds, for example, the Grassmann manifold. Thanks for your attention. If you have any question about our work, online change point detection on Riemannian manifold with Karcher mean estimates, please do not hesitate to contact us.